All right. All right. 15. We'll wait a minute or two. I don't know if currently in meeting. I guess technically I count. Look at all. But it's recording now. So, and some people found the YouTube video for one of the videos. I don't like this chair. I can't. It's my wife's chair. So if I change the setting, she'll be mad. So I'm stuck uncomfortably. Oh, echo. Yeah, it's not that easy. All right. So, what? You're good? Go away. All right. I just want to go back a little bit. It's been a month. So some of the stuff from chapter 7 is important. So today we'll probably do a bunch of stuff that talk about things that are just to remind everybody this is what we're talking about. So when we go back to chapter 7, oh dear, I need to turn that off. We talked about valence and core electrons. Core electrons, when we did a configuration, is the noble gas part. The valence electrons is this outer edge. It's the stuff that does all of the work. In an ionic compound, we talked about counting valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Can everybody see all of this? What I'm doing? Oh, okay. Just because I've never done this before. I see Matt's down here. I don't know why he's. Oh, I guess I can do that. Right, sure. I don't know. It's probably whoever's talking. Go away. Learning by doing. We talked a little. We did electron dot diagrams or Lewis diagrams, and we just put the number around the edge. This is going to come into play, the octet rule, and I can put all these notes up later too. Just even though everyone should, well, you should have them, but they could be sitting in your locker, locked away. Um, Everything wants to have the electron configuration or have the outer shell of a noble gas. So we had metals form cations because they lose electrons. I don't know how to turn that off. I'm sorry. I'll try to figure it out later. So we just basically remove them. Then we can do electron configurations with molecular bonding or covalent bonding. We don't really talk a lot about electron configurations. Uh, where were we? Oh, anions are negative ions because nonmetals gain them. So sulfur becomes sulfide, nitrogen becomes nitride, and all of that wonderful stuff. And this is what we did in chapter 7. This naming transition metal ions is going to come up in chapter 9. We did all that. And all that. Polyatomic ions we'll talk a little bit about. So an ionic compound is a positive and a negative ion. And just so it's over here. Whoa, how did I get way down there? I want it to be way up here. So ionic compounds involve transferring electrons. Wow, that jumped a little bit. So we had sodium, had 1 valence electron. Chlorine has 7. Oh, every once in a while I get a reverb or something. Oh. So sodium gives this electron up and goes over here. This becomes sodium plus. This becomes chloride minus with technically 8 electrons around it, and they pair up based on the number of electrons that are transferred and how many we need. And when we did this, well, we first started with something simple, and then we did calcium phosphide, where we had 2, and this needed 3, so we kind of had to keep going. This all ringing a bell to some people. Yes, no, maybe. Okay, good, because it's been a month, so hopefully we remember a little bit. The important thing for an ionic compound, oh, I think our iPad is plugged in and it's starting to get notifications and it's confusing me. So with an ionic compound, it's all about charges. We have to say, well, I need 2 plus 1s because each sodium in that case is plus 1. So we get 2 positives, each oxide is 2 negative, and those kind of balance out. And that's the fundamental bit behind ionic compounds. Beryllium becomes 2 plus because it's in the second group. Fluoride becomes minus 1, so we need 2 of those, so our formula is BeF2. And fundamentally, that's naming and writing formulas for ionic compounds in chapter number 9. And I think that's kind of really where we finish that. We didn't do metallic bonding because it's not really interesting. That keeps changing page.
How do you go back to what you do with potassium bromide?
Like this one.
Like, yeah, how do you know that bromide is correct?
Your periodic table. So I just need to, I'm going to go switch the slide up here. Remember when we talked about way up here, valence electrons? So like sodium is here, or potassium has 1 valence electron, and bromide is way over there and has 7. And I mean, if I'm going too quick or you forget something, like this is why we're kind of starting with this. So this wants to get rid of that one and become plus 1. This fundamentally gets transferred over here. We add 1 and this is minus 1. And when those charges balance, when all that transfer is the right amount of electrons, everything is quote unquote happy and has that 8 valence electrons, whether it's from losing or gaining. And things on this side lose, which I don't think that's kind of hard to see. And things over here gain. This group we kind of ignore. Well, that's not totally true about down to there. Those ones don't usually make ions, calcium, silicon, and germanium. Tin and lead can, because anything under the stairs, all of these ones kind of act more like they're transition metals. These can make ionic compounds because, well, lead is a metal. There's hopefully not lead pipes in your house unless you have a house that's 150 years old. But hopefully that's been kind of taken out. Tin foil. You've never really dealt with any of the other elements because they're not very safe. So we have all of these metals and a handful of nonmetals and polyatomic ions, and those make up ionic compounds. And there's one thing down here when we talked about ionic compounds. There's a kind of little lab that we could have done. Ionic compounds are crystals. They're strongly bonded. They're rigid. Most of them conduct electricity when they're dissolved in water. Ionic compounds, fundamentally, most of them dissolve in water because water can kind of pull it apart, and we'll talk about that, I don't know, June-ish. So that's a whole bunch of compounds, but you have things like water. Well, that doesn't dissolve. You have sugars, it dissolves. That's sucrose if you put sugar on your cereal or your coffee. It's a whole bunch of stuff, but none of those have metals. So there's a whole other type of compounds. So that was there. So metals are transferred. Anything involving a metal makes an ionic bond. Metals don't mix. There's an alloy. When we have two nonmetals like water, carbon dioxide, methane, hydrogen doesn't want to just straight up give up its electrons. Oxygen certainly won't. So we have a whole other certain type of compound. Sorry. So what these things do is they don't actually, there's no transfer from the oxygen to the hydrogen or vice versa. They're nice. They play better. Oh, so they share. And ionic compounds is like the bully stealing your lunch money. A molecular compound is like, okay, well, I don't have enough money to buy this, and Matt doesn't have enough money to buy this, so we pool our money and we share something. So these are where you've I've heard or said covalent bonding. Covalent bonding is all about sharing of electrons, and there's hundreds of thousands of molecular compounds. Anything that doesn't have a metal is fundamentally a molecular or covalent compounds. So ionic compounds we called formula units, which is the smallest. You have millions of sodiums, millions of chlorides, but there's one for each of them. But in a covalent compound, they're straight up molecules. In water, we know it's just that. There's all sorts of those units. So the two type of IR molecular compounds, which are one homonuclear and heteronuclear, or oh, I don't know if there's another E in there. Oh, apparently I've got those in the wrong spot, but the words are right. Homonuclear, and it's the old different, same. If only I didn't get distracted. So a heteronuclear compound is water. Oxygen and hydrogen are drastically different. A homonuclear compound is oxygen gas. The air that you breathe is mainly those two things. There's a whole bunch of O2, that's the oxygen your body uses, and there's a whole bunch of N2, or nitrogen gas, which you breathe in and breathe out, and it doesn't do anything. So, other than we need to know that quickly, molecular compounds are kind of the opposite of ionic compounds. Ionic compounds have high melting points. Molecular have low melting points. Ionic compounds are all um, generally crystalline. We have two different types, which we don't really need to worry about. Um, they're poor or non-conductors, even if they do dissolve, because a lot of them don't dissolve. And we'll talk about that quickly at the end. These three pictures here, this is the structure that all the girls like. I'm sorry, generally speaking. Diamonds. They're pretty, they're shiny. All of the carbon atoms are rigidly held in place. This is boring. This is in your pencils. It's you peel when you write on a piece of paper, you're basically peeling layers off graphite. This one is the most recent type of carbon. The first one that was found is it's actually a molecule with 60 carbon atoms. Nuts. Did I get the R in there? Buckminster. Yeah.
Wait, what are these?
Yep.
Okay.
Am I going too quick?
No, it's okay.
You sure?
Yeah,
Do we
I've got
have
this.
these notes?
They are all. Sorry. Wire. There we go. So all of these.
Like, we don't have these notes in our book, do we?
No, I printed these, but they're sitting way back in my room, and I. But there's a digital copy of them right there. Well, yeah, and what I'm going to do at the end when I finish is I'll save it as a PDF and post the completed set too.
Oh, sweet.
So, I mean, I'm not going to, I mean, oh my gosh, this sort of thing is just fun things to know. Um, this next part is going to be fundamentally important when we do equations. Um, but those are just molecules of carbon. This is crystalline and very rigid, and you, if you didn't know it was diamond, it's got a crystal shape like an ionic compound, even though it's all carbon. Graphite is soft, um, black, boring. These are, if you've heard the term carbon nanotubes or something, they're all based on these. They were discovered sometime, I think, in the 80s. Uh, Epcot Center. Anybody ever been to Epcot Center? I'm, I, I assume somebody's been. You know the big dome at the entrance to Epcot Center? The big,
Is it like
it,
Disney World?
yep.
Wait,
Oh, yeah.
It's like, I think it's like Spaceship Earth or something like that, or a soccer ball. That's not the best picture. It's kind of hard to tell, but this is a sphere. It's well, it's as perfect a sphere as you can get for 60 carbons. But Buckminster Fuller was the last name of an architect in the early part of the 1900s, and he designed, for people my age, there were geodesic domes at Expo 67 in Montreal. Not that I was alive in 1967, but um, in the Epcot Center. And it's fundamentally like if you look at the old black and white soccer ball, it's going to look like that. And it's just ironic that 60 carbon atoms stuck together like that. So the general term for any of these C60, there's a C70, and all of that are fullerenes, and then they make nanotubes and all of that stuff out of them. But it's all based on sharing of electrons. And where we start with the sharing are diatomic molecules. The single most simple molecule in any sort of science is H2, two hydrogen atoms. Hydrogen in nature exists as H2. It doesn't exist as H because, well, that has one valence electron. It doesn't want one valence electron. It wants to be like the nearest noble gas, which is helium. This, we've got hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those have seven. They want one more. This has six. It wants two more, five. These things all pair up, and we're going to talk in a sec about why and how. But you need to know that those eight, you never use astatine because it's ridiculously rare and man made. But these all exist in nature, and they all exist in nature. These are all in your air. Those ones are perfectly stable. They don't really exist in air because those are will burn you and kill you. That's a brown liquid and a purple crystal. But you need to know that the diatomic molecules, there's a couple of kind of mnemonic things. BRINCL. It's those things all in a different order. Brinkelhoff tells you that, or the other one is I, and this is bring clay for our, and that's kind of in order, I, B, R, C, L, F, O, N, H. Well, it's in reverse order, I guess. These exist when we get to the further chapters. If I say, oh, I want to know how many moles of fluorine there is, we're talking about F2, not F, or what a molar mass or something is. Those exist as diatomic molecules. There's other things that are they're heteronuclear, but they're bigger. There's, wow, that was a really bad 4. Phosphorus can exist as a bunch of things. Some phosphorus is just a boring plain chain, but then you have these neat little tetrahedrons of phosphorus called P4. Sulfur, the stinky stuff, yellow, exists as S8. And generally, if I want you to use P4 or S8, I will let you know. But the diatomic ones, like these are, you need to know that those elements are diatomic. And we'll talk about them. Molecular compounds, I said, I think it was either up top or on the last page, they're distinct units. The formula tells you, shows the type and number of atoms that are present in a molecule. There's no lowest ratio, there's no simplifying things and all of that. C6H12O6, well, that's a whole bunch of things, most commonly glucose. It's the sugar your body uses. There's a couple of forms of it. What we need to know in chemistry, I mean, I'm not going to ask you to name that, is that this isn't, it is 6 carbons, 12 oxygens, or 12 hydrogens and 6 oxygens. Mr. Bellier, if you asked him to draw the structure of glucose, he'd be able to draw it for you in a second because it's part of biochemistry, but it's chemistry. That's my thing, and I don't care what the structure of glucose is. It doesn't tell us anything about how they're arranged because I say glucose, but if you've seen on food packages, glucose, fructose, well, fructose has the exact same thing, or formula, but they have different structures. So that's a biochemist would know that, or an organic chemist. I'm not all that worried about them because we're not going to do a lot of stuff with that in grade 11, even grade 12. I think grade 12 biology, you need to know a little bit more about that. So how do these things form? So we have a hydrogen has 1 valence electron. This tells me there's 2 of them. So I need a second hydrogen atom. And when we did chapter 5, I think we talked about orbitals and all of that. So this is, we could do an electron configuration, whatever, it's 1s1. So we've got an electron effectively floating around this, and an electron floating around that. So, oh, that's, just a sec, I need to group that because for the visual, and because it's being videoed, then everything will be kind of make a little bit more sense. So we have hydrogen, and you get closer. They get closer and closer until eventually those 1s orbitals overlap, and you have that pair of electrons. Now, is this going to work? Shoot. Bring to front. So hydrogen as an atom, if we go back to the periodic table, it's 1s1. It wants to have 2 valence electrons, so it's like helium. It could technically get rid of that, well then it has none, or it could add one. But how many electrons are around that blue hydrogen right now? 2. Now I can look at it the same thing. How many are around the red hydrogen? 2.
Two.
So now, is this hydrogen atom happy? Because it kind of effectively has 2 electrons. Its octet or whatever is full. This hydrogen atom has 2 electrons. So they share them. Covalent bonds, nonmetals want to hold on to their valence electrons. They don't want to give it up. Um, they still want that, so they share their valence electrons with each other. By sharing, they get that noble gas configuration. And I think we'll talk about, I don't know if this call is going to cut off at 2:30 or not. I have no clue.
Wait, so they don't necessarily like combine, they're like
Nope.
just sharing.
Yeah, they just share, they stick together. When we talk about, well, like, there's all sorts more to this, but the hydrogen atoms will basically get close enough to each other that the electron from this one is close enough to that one so they feel them. They can't get right on top of each other because the protons in the nucleus eventually will push away. But they get close enough, and if I do this, like there's a particular distance, and we draw it kind of like that. I don't know how far those distances are. When we did atomic radius, basically an atomic radius is they figure out how long that bond is and cut it in half and say, well, that's the radius of this one, that's the radius of that one. It's not the best thing, but it kind of works. So that's hydrogen, and I'm just going to do fluorine is the one on the bottom, and then we'll stop because it's Good Friday and Lewis structures are going to take a little bit more time. So this is the gist of molecular bonding. It's all about sharing. They don't want to transfer. There's some like electrons more than others, and that's something we'll talk about down there. So fluorine is a little bit more complicated because fluorine has 7 valence electrons. Fundamentally, it's the exact same idea. I just want to make sure I got that. The second fluorine has 7 valence electrons as well. They do the same thing until we get that overlap, because that box was there after. How many electrons are around fluorine? The blue fluorine. 8. And then the red fluorine has 8. Where we'll go eventually is when we get into, well, what's the word I'm looking for? Just trying to think of one because hydrogen is a pain in the butt. Technically, I can write a molecular formula for a compound that's OF2. And we'll look at how many electrons they need, how many bonds they have to form, and that's what happens as we go down here. We'll talk. That looks like a whole bunch of stuff, but it's really not all that difficult in the long run. So, is that a good start? Does that make sense logically? Yeah, it's
Some of them.
yeah. And chemistry is that I've said it all semester. The problem with chemistry is you can't see a fluorine atom. I've never seen a fluorine atom. I know that this works because everything else works, but it's all about that model. So let me get rid of that. Sure. Does anybody want the notes from chapter 7? Just I can post those up there. So if you wanted to look at them, because if you don't have your books at home, um, that might be a little bit difficult. Wow. We got a good amount of people here today. What's going? Oh no. Erasing. I don't want that. This is what I wanted. Yeah, I'll take 17 people. That's not bad for a Friday afternoon.
Got
So
nothing better to do, buddy.
you can go shovel snow. I just want to stop here because this Lewis structures for bigger things, like that's a kind of full. That's going to take another 45 minutes or so, and it's not that I don't want to stay here. It's that there's two other people who need it. Well, Kate is napping. Ben is probably driving my wife nuts, but that's what toddlers do. So, any questions on that? This is kind of
Where
in
are you gonna post it?
uh, back in the like I'll post it back on the Teams page. Uh, what we kind of talked about today is the stuff in 8.1 and a little bit into 8.2, but we'll get into. I don't like how some of that is done, but we'll deal with that as we go. So if there's no other questions, I'll save this and make my third YouTube video, which is kind of exciting.
Like, do we have to do it? Well, like, there's like 8 things, but like, what has to, what's due?
uh, we'll go through like we're gonna have to do a little bit of what I may do in like the textbook is like there's questions at the end of each section. Um, and there's some things we need to be able to make sure you can draw a dot structure for them, and that's what that Lewis structures thing next is. Some of it's just going to be questions from the book. Oh, do the questions from the book, take a picture, and when I put an assignment up there, um, I'll post something in that chat part. Like if I say, if I'm looking for certain questions, I'll make an assignment. I don't know why that's showing that. Why am I? Oh, activity. Where'd that
You
chat
trying
thing?
to chat with me, McKay?
No, it told me you joined. I don't know what the heck this is. Like, I don't know. Teams echo user added. I don't know what that means. Hmm. I didn't even notice the chat thing, but sorry, I meant the in this kind of stream if I'm looking for questions to do, and they'll it's not like will be like, oh my gosh, do these questions, I want them done for tomorrow. It'll be like kind of a progressive thing, if that makes sense. Yes, no, maybe.
So like, you're just gonna click these questions like throughout,
Yeah,
take a picture and send it to you.
yeah, they're in the assignments thing. When we get to it, I'll go through and show how to, or as far as I know, how to submit something. But
So
we'll,
we have nothing to do like this weekend or anything.
no. We just need to check when we want to come back. Are we going to do Tuesday or Monday? It doesn't make a whole lot of difference to me
Let's do Tuesday.
Yeah, I say Tuesday at 2.
because you guys may have.
If it's up at home, so even if not, I can meet.
Ah, sounds good. Anybody else have any concerns, problems? Everybody else happy? Ready to look for Easter eggs at some point? Or, I don't know. I would just, if this was when kids were older, I would just go throw them in the front yard and it's like, go dig through the snow.
I didn't even think of this thing.
Yeah, we're from Washington.
Well, it's, but if you wanted, like, you can read parts of like the first two sections of chapter 8 in the book, but that's the only thing I would say you would need to do for today. So we all good?
Think so.
Okay. Perfect. Have a good afternoon. Enjoy your weekend. No problem. See you later. Bye.